Hello, I'm Dr. Neeraj Magotra, Chair of Electrical and Computer Engineering Department, and I hope all of you and yours are staying safe during this coronavirus crisis. And much as I would like to have you here in person, needs must, and so I would like to welcome you all to our virtual open house. Here's my contact information in case you'd like to reach out to me, and now let's get on with the show. That is, by the way, a picture of me before the crisis.
Okay, thank you, Dr. Magotra. So essentially, one of the things that we want to go over briefly is why study electrical and computer engineering at WNE. Again, we claim that we are very student-centric, as we will show later in this video. Our equipment, again, will also show that it's very accessible. So again, labs are always open, pretty much from 8 a.m. to midnight. We have experienced faculty that we will also sort of demonstrate in this video as well. And then we also have very strong industrial connectivity. So internships are a huge part of what we offer. Most students in their sophomore, junior years, going into those summers, they get internships. We sort of built an alumni network where, we have students and graduates that are placed in various locations throughout, mainly New England, since we are more of a regional school. And we work for companies such as BAEs and the Raytheons of the world. We're able to place people across all these places at various internships, both electrical and computer engineering. Again, just to sort of summarize the two degrees that we offer, Bachelor of Science in Electrical Engineering, Bachelor of Science in Computer Engineering. One of the things that we wanted to highlight is that depending on your AP credits that when you come in, we do have a number of students who are graduating within 3 years if they are ahead in math, specifically AP Calculus. So when you do attend summer orientation registration, come seek us out. We can sort of see if that's something that you can fit into. We also even have some students who are doing the master's program, which typically takes 5 years and 4 years since they're on this sort of accelerated path. So these are the things that we're looking to sort of get on the ground rolling. So if you do decide, obviously, to come here, these are sort of the discussions that we can have. And again, feel free to reach out to any one of us and we can have those conversations as well. And then again, in summary, sort of our motto for our department, we believe that this hands-on approach effectively prepares our students. 100% of them get placed in jobs or grad school. We feel that it's a very good community here. So without further ado, to sort of speak to some of the stuff that we discussed earlier, I'll have Spencer sort of describe his experience here at Western New England.
So. Hi, my name is Spencer, and I'm a graduating electrical engineer in the ECE major here at Western New England. I'd like to tell you a little bit about what your experience will look like here over the next couple of years. As incoming freshmen, you'll be exposed to the fundamentals of engineering. You'll be introduced to the basic concepts of engineering, teamwork, and design through the use of hands-on projects and classwork that'll set you up for success for the rest of your time here. In the fall of your sophomore year, you'll learn how analog circuits work as well as how to analyze them. You'll also learn how to measure and record real data using the equipment to improve on the fundamentals. In the spring, you'll switch focuses to the digital side and learn how the concepts you learn in the fall will apply to the digital world. Going into junior year, you'll start focusing on some of the more advanced concepts of the major, taking classes like electromagnetic fields and waves, microelectronics, and digital signal processing. You'll also get to experience the junior year engineering lab, where you'll get to put all those skills to good use. Junior year is also the time where you'll get more choices about what you want to learn, allowing you to focus in on what interests you as an engineer. Finally, senior year is where everything you've learned comes together. You'll participate in a department-wide project with your classmates, where you'll design, build, and program circuits for a remote-controlled car. You'll also do your own senior design project, a capstone project that reflects the skills and knowledge that you've learned over the course of your enrollment here, resulting in a project that's uniquely yours. As a graduating senior, I'm excited to start my career and apply everything that I've learned from Western New England University.
Essentially, to piggyback off what Spencer said, what we have here is actually the senior project that is an interdisciplinary project. It's actually our Lab 3, so it consists of taking an RC car, completely taking all the electronics out of it, and then essentially what we do is we work in teams to rebuild the electronics for it. So every electrical engineering student is paired with a computer engineering student team, and essentially the electrical engineering student teams, they design an electronic control board. They also do some signal processing and filtering and signal conditioning for the computer engineering board, which takes data from various sensors on it. And then the computer engineering board, what it does is it also has an electronic control unit, both implemented using pulse width modulation, so that either the computer board or the electrical board can take control of the car and drive it. All right, so again, just giving you an idea of sort of the integration between the electrical and computer engineering curriculum for a interdisciplinary project. Okay, now next we'll hear from actually Tim Hayden, who will give you a description of what he's working on for his senior project as some of the offerings that we have. Thank you.
Hi everyone, I'm Tim Hayden, and I'll be presenting my senior project, the development of an Eog Control System. I worked with Josh Minuskin on this project. We are advised by Dr. Ronamai, and we are sponsored by Bose. A quick overview of what I'll be covering today. First, a problem statement, followed by a system overview. After that, I'll discuss the hardware and software used in this project. Lastly, we'll end with a video demonstration. The problem statement or issue at hand. Patients suffering from neural diseases lose the ability to move and speak, but retain their eye movement. Using eye movement to communicate with devices would greatly improve their quality of life. Other applications of capturing eye movement include activity recognition. A system overview of the EOG control system. The control system uses electrooculography, or EOG for short, a method to measure electrical activity generated by eye movement. EOG signals have a small amplitude on the order of microvolts and operate at very low frequencies. These signals need to be manipulated and conditioned in order to be used by an Arduino microcontroller. The Arduino microcontroller processes these signals in MATLAB and uses those signals to navigate a test bench, or in our application, a grid. Here we have the hardware used to acquire the EOG signals. First, we have the EOG acquisition board, which is on a PCB. This board sits on top of an Arduino microcontroller. Attached to the board, we have all 4 channels and a reference channel for a total of 5 channels, which is connected to a bioamplifier, which has snap electrode connections on them. For this application, we used a 5x5 grid as our test bench. The green grid depicts the current grid the user is on. The yellow line highlights the next direction for the user to look and is chosen at random. However, it won't pick a side that results in the user leaving the grid. For instance, if the user is in the first column, it will not pick left to go. It'll either pick up, right, or down, assuming it's not in a corner grid. If the user accidentally looks in a direction that would result in the user leaving the grid, the program will print an error message warning the user you cannot go in that direction. Lastly, we have a demonstration of the EOG control system. The participant in the video is another student who has agreed to participate in this research. Here we have a left movement. You'll notice he just looked to the left and the grid changed to left. And right here we just have right movement and just move to right as well. And you'll watch as he moves, the system picks it up pretty quickly, and he continues to navigate the grid with ease. Hardware similar to this can be used in a wide range of applications for the disabled, perhaps even using additional bioamplifiers. Thank you.
So essentially the next view that we're going to look at is actually the Sophomore Lab. So every single lab bench is equipped with a power supply, an oscilloscope, function generator, multimeter, workstation as well. All the components you see against the wall are all open available. And this lab space itself is all open and available to all students starting at 8 a.m. to midnight and even past those hours. You'll also notice that there's only 2 seats per bench, so everyone only works in pairs of 2. And again, this is primarily used for sophomore labs. So the next piece of lab space that we have adjacent to the sophomore lab is the junior lab. You can see it's set up a little bit differently. We have the row of tables that sits in the middle. The workstations are against the outer perimeter of the wall. Again, primarily juniors and seniors use this lab space. And again, it's pretty much equipped with the exact same equipment. The oscilloscopes are a little bit different, and the function generators have a little bit more functionality compared to the sophomore lab. But again, this is all workspace that our students use. It's all free and open. And coming up next, Dr. Ranamai is actually going to give you a demonstration in the controls lab for some of the other projects that we work on.
Hi, my name is Kurosh Ranaway. I'm a professor of electrical engineering at Western New England University, and my areas of specialties are in artificial intelligence and control systems and automations and robotics. I'm going to give you a quick demo of what we're doing in this lab. Most of it is actually 99% is the project base on senior projects, capstone project that students do. I'm going to start with this basically roll access for a flying machine. If you have a flying machine, it will basically rolls on one axis, the other axis, and then it will do what we call yaw, and goes up and down in different directions that you want to go. This demo is just only for the roll axis, one axis of it, and for the safety it's harnessed so we can experiment with it and make it actually go wild. And that's what's interesting part of it is that you see this system is unstable and we have to stabilize it. And by itself it would not perform, when we say unstable, it will not perform nicely. It would be actually a very bad performance. So with the help of the computer programs, we can program this, have a computer that actually controls the behavior of this system. What I have over here is the roll axis. Another example of it would be this airplane, which is basically Armed Forces vertical takeoff landing airplane that basically can take off like an airplane. It has two big engines that rotate and turns it into a helicopter. After it takes off, the engines rotates and becomes an airplane and flies. So this would be the roll axis, and the most challenging part of this is when this aircraft tries to land. During takeoff and landing, the most critical point of flight that you can have. So this is simulating the roll axis for you. And I have a joystick over here that I can basically maneuver and give it a command that goes to the one to the left side in this case, then goes to the right, and I can hold it and stays over there, and everything is nice and stable. This computer program over here, which students, we use these tools for students that they use from a very high level graphical interface. We can go right into the second computer that actually controls the behavior of that system very nicely. Now what I'm going to do, I'm going to take the computer control out and make it only me trying to control this system without the assistance of the basically the computer. The moment I do this, this system goes into a, without me doing anything, goes into a violent behavior, and it basically tears itself apart. If this was an airplane and it was close to the ground, the airplane would be destroyed. So just by my input, trying to control this thing, doesn't matter how quickly I try to respond, it's not fast enough. Our response and behavior is not fast enough to control this kind of machine that is unstable, and that goes with these flying machines too. We have it, multiple generation of UAVs that we work over here on the projects that we're doing. So that's a perfect example. Students work on this. This was a senior project. Students developed it, and it went through many generations of it to a point that is very nicely. Students can experiment with it, do senior projects, and we did some AI on this, that when this airplane close to the ground and a gust of wind hits it, the computer basically takes over, tries to help the pilot so it would not crash and it would not, a bad thing would happen to the airplane. So we did all that senior project for it. So this system is the basis for all the robotics and motion control and things that you see in factory automations and assembly lines and robots, basically this system duplicated for multiple axes. And basically what we're doing, we're commanding a motor to go between two positions. So if this was, for example, a robot arm, we're commanding it to go from one point to another point, going back and forth between 2 points. So the whole purpose is that when we're giving a command to a robot arm to move, we want to get to the point that we want it to go very quickly, but we don't want it to start oscillating back and forth. So the faster it goes, the more it has tendency of oscillating. So creating a sophisticated algorithm for controlling it, we can kill that oscillations and make it behave properly. There are many different algorithms that you can use at different levels, and I use this system for teaching classes, and students do projects that they come actually in the lab and implement their designs, exactly what you see, and see what they designed with their Simulink or the software simulation, actually working on the real system in the laboratory. And as you can see over here, in this particular case, the motor goes back and forth between the positions very nicely. And if I try to see whether I can change the behavior of it by changing one of the behaviors for the mathematical model. And if I take in this particular case, my feedback would be math feedback. So I'll go back over here into my system. And try to manipulate it. In this case, it's sitting at 1. If I try to increase it, as you can see, the system starts oscillating, and the oscillatory behavior of the system, you can see it very nicely by changing that. So I took it basically off the design that we had done mathematically on this system. So if it goes off, as you can see quickly, the system response gets really bad. So the whole process of coming up with these controllers, that's what we call a control system. So feedback loops that we are creating over here, control system such that it behaves very nicely, very quickly go between 2 points without starts oscillating back and forth. So this is a basis for all the robotics. I use it in all my classes, and it's been very successful. Students like it very much.
All right, thank you, Dr. Anamai, for that. So next lab that we'll take a look at is actually the 3D printing and wireless communication lab. So effectively what we're showing here is just some of the equipment that we have. So we have a router. We have this Quiddy 3D X Max 3D printer. Again, the build space on that is approximately 12 inches by 12 inches. So that's primarily what we use for all our 3D printing capabilities. We also have a couple of smaller 3D printers that we can also work on. Currently those are being fixed. Again, these are very cheap and it's easy to get replacement parts for them. So again, some of the students tend to work on those. And then on the other side of the room here, we actually have our 3D cutter on the left side there, and then we have our various network analyzers and RF components that we use for our labs. So this is part of our mechatronics offering. So essentially what you're looking at here is a robot arm that was built back in the 80s or whatnot that was used for advanced manufacturing. So a lot of this has been student work where we've taken a lot of 1980s technology and we've sort of gone through and upgraded it. So the real emphasis here is on combining electrical systems with computer systems and really embedded systems. This has really become a computer engineering project with some of the electrical engineering aspects in it that are needed for motor drivers and so on and so forth. So again, another multidisciplinary project that we have here and something that our students work on together. Okay, so again, we'd like to thank you for spending some time with us today. Again, these are the faculty members in our department. If you have any questions, you can find us on the web. Feel free to reach out to us via email. Specifically, you can get in touch with Dr. Magotra as well. We'd be happy to answer all your questions, and obviously we look forward to you starting your career and journey as a Golden Bear. So thank you for your time.